Okay. Hello, my name's Tom Russell. I'm a research software engineer based in the University of Oxford. And I'm going to talk briefly about NISMOD, the National Infrastructure Systems Model, what it is, how it fits into DAFNI, and give a couple of examples of some results that come out of this analysis, just so we've got a bit more of a concrete idea of what we're talking about. Okay, so here's a picture of NISMOD and DAFNI from a high level, with a bit more space given to the models that interact in the middle. So we've got a set of infrastructure system models, as Jim mentioned, and there's some data interactions, some coupling between them. And the way we frame our analysis, typically we introduce some scenarios of uncertainty, so population change, the economy, land use, and climate into the future. And then we consider some strategies of infrastructure provision, where that's building new stuff, introducing demand management, behavior change, improved efficiency, changing technologies, or other spatial planning. And all these come in as parameters and data sets that feed into the models. So they come from, they're loaded into DAFNI's NID, the National Infrastructure Data Store, and loaded from that into the model running framework, and then they give us out some metrics of future infrastructure performance, where that varies enormously from model to model, but can give an idea of typically something about the security of supply, so how well these systems will provide the services they're intended to provide into the future, the affordability of that provision, and perhaps carbon emissions or other environmental metrics about how well they sit within society and the environment. So that's the big picture framework of what NISMOD is intended to do and how it sits within DAFNI. From a slightly more technical point of view, what are the bits and pieces here? All of the code is on our NISMOD GitHub organization, so feel free to have a look at that and browse around there. Each of the models are separate repositories, and there's a repository called NISMOD 2, which holds the configuration that couples everything together. From the research side, I should flag the whole series of webinars that we did as a consortium last year, and that tiny URL link should point you to a series of other talks that go into much more detail than we could do here on each of the sectors, and indeed touch on the international and risk and resilience parts of the research as well. In terms of representation, Jim mentioned that these are spatial models. They typically have a representation of some network, and here's a sketch of the water network in the water supply model, the electricity transmission network, and the major roads networks. And these are national models at the scale of at least England and Wales. Others, depending on data availability and the way we can set up the models, cover all of Great Britain or all of the United Kingdom. And then finally, in terms of how we plug these things together technically, we have a package called SMIF, which is a simulation modeling integration framework to handle the configuration and specification of precisely the inputs and outputs of these models. So when we've uploaded each of these models to DAFNI, we've wrapped them in the metadata specification for SMIF, packaged them into a container, and placed them onto the NIMS, the National Infrastructure Modeling System. So we have national models, but we can look in some fair amount of detail at specific regions. And I wanted to touch on the Oxford-Cambridge Arc, or so three pieces of work we've done in the Oxford-Cambridge Arc. So firstly, what is the Oxford-Cambridge Arc? The National Infrastructure Commission wrote a report a couple of years ago setting out ambition for housing growth and transport link improvements in this area broadly from Oxford to Cambridge, but including a couple of other counties up to Peterborough And so this is a good example of a possible piece of spatial planning that our networked infrastructure models can represent and ask interesting questions about, particularly because it's importantly linked to its context. So the initial driver of housing growth comes partly from an ambition for the area, but also from recognizing pressure from London. There are internal migration links around the country if we did see a large increase in population in this area. The freight routes proposed stretch from east to west beyond the corridor. So this is a corridor that would be traversed to other parts of the country. And as you recognise, the major roads run north to south through the region. And in terms of the utilities, the water catchments don't fit neatly into this identified arc, and there are effects beyond the borders of the region. Similarly, the electricity transmission grid reaches across the country. So this is an interesting case study to look at specifically within the region, but also recognising the wider effects. So on that, there are three bits of work that I'll touch on just now. A report we released last year, running each of the infrastructure sectors and looking across the corridor. Then a further bit of work we did with England's economic heartland and colleagues in the University of Southampton, specifically on the transport sector. And then more recently, a piece of work with colleagues in the University of Newcastle, looking in finer detail at possible future patterns of urban development. So from the water model, in that analysis of the Oxford-Cambridge arc from the ITRC report, we considered future population and climate scenarios, and the kind of results you get out are broadly that population growth will increase water demand despite per capita reductions. So we considered the water companies' baseline case and their demand reduction case. And as you can see on the left, risks of a drought year are considerably higher than if we reduce demand across the board. And we understand that the near future climate scenarios are a considerable contributor to the increased risk of water use restrictions. On the other hand, each of the coloured bars here represents a different option that we considered, and in each of the different regions, some of those options reduce risk a considerable amount. So there are large interventions available that we could introduce into the model, into the system, to avoid some of those risks. Looking briefly at the transport model, so there's a representation of the network within the arc here. We looked at the scenarios of one scenario of future population and several scenarios of future behaviour and policy change around transport. The significant option we considered away from the baseline was to introduce or to switch all passenger and freight vehicles to electricity or hydrogen, so carbon neutral fuels. And sure enough, we find that switching to electric vehicles would reduce transport emissions and increase electricity demand. And you see that in the two graphs on the left. But we also note that without in the absence of other drivers to reduce demand for private vehicle use, congestion and travel times and travel speeds increase across the network over time. So we can look at, this is an example of imposing scenarios and strategies and looking at a series of different metrics coming out of the model. But yeah, again, I can encourage you to look at the report for plenty more detail on this particular piece of analysis. So finally, from this set of examples, we looked at urban development scenarios. So the idea that we could introduce a headline number of houses to build within the ARC, and what the model, the urban development model here, represents attractors and constraints for the location of that housing, where there are a lot of options, as you can imagine, that you could introduce different sets of constraints or weight different attractors more strongly. So the first map on the left shows ecosystem services within the ARC, where dark green areas have high non-food natural capital scores. So this is everything from habitats to recreation to flood protection to carbon storage. And the deeper yellow areas show areas with high food production natural capital scores, where these are high grade farmlands and fields. So one of the constraints and elements that we introduced to the model here was to avoid building over areas with high natural capital scores, so to aim for good environmental outcomes. Then the two maps over on the right show two extremely different options for that development. One which is much more diffuse and focuses development around existing settlements, particularly broadly around the Oxford, Milton Keynes and Cambridge areas, and another which is much more focused and drives development in a planned way towards potential new settlements. And we get metrics out of the end of this, looking at how much land is taken and the impacts on ecosystem services scores, the accessibility of those new developed locations to employment or to jobs. Okay, that was a bit of a whistle-stop tour through the kinds of model runs and connections that we can make between data sets with NISMOD and within DAFNI. I hope it's been a bit of motivation to introduce what's possible and what's available within the system. So just to summarize, NISMOD does integrated infrastructure systems modeling. It's a set of national models that can do regional analysis, which allows us to set results in context and dig into detail in the areas of interest. We can drive a whole series of scenarios to account for future uncertainty through these models, and introduce different strategies for analysis. And within and between the models, there are these interdependencies. So I touched on the electrification of heat and transport, and the dependency of the energy and water models on climate variability. That's all I wanted to touch on. So on the right, this sort of repeats the workflow idea, where there are a series of data sets that we connect to, and a series of models that are coupled in different ways. And Rose and Martin will demonstrate that much more practically in the DAFNI system in the rest of these presentations. Thank you very much.
Thank you, Tom. So